Hello students, I'm going to show you how to calculate the rotational inertia of a thin rod rotating about its end perpendicular to its axis. Now the equation that we're going to use to get started is the equation that allows one to determine the rotational inertia for a continuous body. There is another method called the parallel axis theorem, and I'll show that, or I'll at least suggest as much at the end of this tutorial. So I is equal to the integral of r squared dm, and for the purposes today, since our rod is laid out along the x-axis, we're really going to take the integral of x squared dm. Now to get started, I'm going to take a little slice of rod. So there's a little bit of width. Take a little slice, which constitutes a little width, and I call that dx. That's a differential length of x. Now contained in that differential length of x is a certain amount of mass, and we'll call that dm, a differential amount of mass. Now, if you remember mr squared being the equation that allows one to determine the rotational inertia about some axis due to a point mass, think of this rod as being a series of point masses. And we could use method of exhaustion, slice this up 100 ways, 1,000 ways, 1,000,000 ways, but there's an easy way to determine the sum of all these little masses, and that's the integral. I won't go into detail what the integral is all about, but simply this is if you let dx go to 0, the number of differential masses goes to infinity, and in a series, sum of all those gives you a nice approximation. But even more, a much nicer approximation of its exact value is using the integral. So let's get started here again. A little long-winded, but so dm dx is x units from the axis of rotation. So I'm going to show this is my x, and also I need to specify the linear mass density, lambda. Lambda is equal to large M, that's the total mass of the rod divided by the length of the rod. This is also equal to, and if this is a uniform rod, at least the uniform distribution of mass along a particular length, it is also true that if I take that little chunk of mass and I divide it by the width, which I've sliced, I should get an equal amount, or the equal ratio of the dm to dx. So, and this is the trick in order to make this integral work over here, because I need to substitute dm into our continuous equation. Dm is equal to lambda dx, and that's the trick. So let's bring our integral down here. So we have I is equal to the integral of x squared, and now substituting for dm, lambda dx. Okay. Now, the limits of integration, the lower bound is going to be the axis rotation. That's going to be 0, and our upper bound will be out to the end. So we're going to add up all the dm dx's from the axis rotation all the way to the very end of this rod. Now, the integral of x squared is fairly simple. Remember, we add 1 to the exponent, and then we multiply that x now cubed by 1 over the exponent plus 1. So the solution is 1/3 x cubed lambda. Evaluating that from 0 to L. Now, if we substitute ln for x, we get 1/3 L cubed lambda minus, if we substitute 0 in for x, we get 0. So it's fairly simple. Now, substituting lambda, or m over L, and for lambda, we get 1/3 L cubed m over L. One of the L's cancels, and we get the rotational inertia of a rod rotating about its end. 1/3 mL squared. And there you have it. That's how you calculate the rotational inertia of a thin rod rotating about its end perpendicular to its length. All right, have a good evening.